In our work with exponential functions, we've seen, the base function, right, b to the x, and then in the definition, remember that b was defined to be a positive real number that had to be different from 1. And so we've looked at some transformations of that, and we've even looked at mainly one specific transformation where it's a times b to the x. So we have a vertical scaling component added on there, okay? And so that's kind of the model that ends up being the most useful for us in practice. The other model is really doing a vertical and a horizontal transformation, which is coming up in our future, but we want to look at this b or a times b to the x model a little bit more. Okay, and remember that I said that b had to be a positive real number different from 1, because otherwise if b is 1, you just get times 1 times 1 times 1 all the time, and that doesn't change the value. It's no longer exponential. Okay, so in reality, when we look at this model, I'll just write it a times b to the x. Really, how many mathematicians look at this is it's still a times b, but then this b has to be 1 plus r. And r just represents a change amount. Something that's, gets you above 1 or below 1, depending on its value. And so this is the other model that we're going to slightly look at, or we're going to look at and change slightly. Now, in this definition, this r value, this ends up being a change. And I'm going to just say it's a constant change. And we know that when we're working with exponential functions, the exponential functions, their characteristic is that there's a constant proportional change. You're always multiplying by the same number all the way throughout, right? And so whatever we're changing by, now we can represent that in this by this r amount, okay? And so, as I mentioned, it is a change amount, but typically when we encounter scenarios where we have to use this variation, we talk about it as the percent change. So we're increasing by, 2%, 5%, 22%, or decreasing by that amount too. So it's represented as a percent, and in practice, when we actually use it, it's a decimal. Okay, so R is equal to a percent change, but often expressed as a decimal. All right. So a, a scenario where this comes up is actually in wages, and so I'll be transparent. My salary as of last year, at the time of this recording on April of 2023, my salary for this year was approximately $72,000, and then on average, historically, I've always received about a 2.5% increase to the salary, and that is just to cover the cost of living. And then, assuming that there's no additional raises or promotions, we want to develop a model for this salary and then predict what it would be in 2053, which is when I would turn 65 and potentially retire. I may retire before then. Depends on how, life happens. But as we look at it, so we know we need to develop a model. So y is equal to, a times 1 plus r to the x, okay? And just to clarify the notation here, we're going to have to find a and r, right? But then y is going to be my yearly salary in dollars, okay? And then x would be the number of years. And I'm going to say that this is since 2022, only because that's the data point that we're provided. So we're looking, after 2022, okay? So y is equal to a is going to be the starting amount. So how much I would have in 2022, okay? So just if you need to make that, sometimes this is called the principal, okay? Oh gosh, AL, no, EL, AL. I don't know, look it up. But this principal is a common piece of language used when you're working with money. It's just your starting amount, okay? So what you would start at, okay? So in this case, it would be 72,000, okay? And then 1 plus, and then R would be how much I change by every year, or how much my salary changes by. And so that is 2.5%, but expressed as a decimal. Okay, so 1 plus 0.25. Yeah, 0.025, I'm sorry. Okay, and then this would be all to the x power. Okay, and so if I do this math out now, so this is the model. Okay, and if you want to give it, f of t, name, whatever, that's fine. And then if I evaluate my salary equation or salary model for when I turn 65 and would retire that year. So let's see, 2022, I would retire in 2053. So that would be 31 years of exponential growth. Okay. And so then if you evaluate this using a calculator, I got $154,000 and $154,800 and 49 cents. That would be my annual salary that last year that I work. Okay. So let's see. Salary in 2053 would be $154,800.49. Okay. So there we go. That's a nice salary. By today's standards, 2053, I'll probably be below the poverty line if things continue the way they are. Joke. But there we go. All right, next example we're going to look at is we're going to buy a new truck right now. Say it's worth $50,000. Okay, I'm not really going to do that. I just paid off my car. But let's say you, as a student, we're going to go buy this truck. I don't know with what money, but there you go. So $50,000, and this truck that you buy, it's a nice fancy truck, but it has a terrible depreciation schedule. It depreciates at 15% per year, and when we say depreciates, that means it loses 15% of its value every year for 5 years. Okay, and so this means, so this 15% is a constant change, a constant rate of change. So when we look at our base exponential function, a times 1 plus r to the x, right, we can say, okay, the initial amount, the principal, what the car or the truck was originally worth was 50,000, but then when we're dealing with this r value, it's actually going to be a negative rate because it's losing 15%. Okay, and so this, if I were to do the math, okay, just simplify things a little bit. Another way of saying if it loses 15% of its value each year for the first 5 years, it would be worth 85% of its value from the previous year. Okay, and so this is scary, but then so that's our model. And then if we figure out the value at the end of 5 years, $50,000, okay, we're almost scared to see what it's worth. And if we put in 5 there, what do we get? Okay, so I'm typing this in my calculator, times 0.85 to the 5th power. Ooh, ouch. Okay, y is equal to $22,185.27. Okay, so I'm just going to write a note. In 5 years, the truck is worth $22,185.27. Maybe that's good to you, but vehicles, they depreciate terribly, and it hurts. So there you go. Okay, and so the big takeaway from all this is that when we're talking about a percent change, right, our exponential function that we've been working with, a times b to the x, gets modified as 1 plus r to the x. And we have to figure out what r is. R is just going to be whatever we change by, and it has to be a constant change over the time interval that we're looking at. Okay, and so again, that r value could be positive in the case where you're growing, or negative in the case where something is decaying or going away. Okay, so just be aware of that going forward as you work with context exercises.